All right, we have this problem with some blocks on a spring. It starts off fairly simple, and then it gets to a point where we've got a little bit of thinking to do just to be clear on what's going on. So we have some blocks that are pushed down and released so that they oscillate. And the first thing we want to do is get the spring compression. So there, we're going to reach equilibrium when the weight of the blocks is balanced by the force upwards from the spring. So for part A, we can, and I'm just going for absolute values here. I know there's a restoration force, which is negative kx, but we're just going for magnitudes. So mg over k is x. And so we can actually put in our numbers 8 kilograms times 10 over k, which is 1,000. And so we're going to get 0.08 meters or 8 centimeters, but we only work in meters in AP Physics. Now, just a couple things. If you look at the period formula on the AP Physics sheet, the period of a spring is given by 2 pi square root of m over k. The frequency is 1 over the period, so that's going to be frequency is 1 over 2 pi square root of k divided by m. And so we can actually put in the numbers. We will get 1 over 2 pi square root of, and for k, we'll put in 1,000. And for m, we'll put 8. And so when we put that in our calculator, we're going to end up getting about 1.8 hertz. All right. Now, this is where things get a little bit more interesting in that it says, how far can the spring be compressed in part A without causing the blocks to exceed the acceleration value? Sorry, determine the maximum acceleration and how far the spring can be compressed. And then we're going to be talking about maximum speed. So there's a couple things that we should talk about here. So before we do parts C, D, and E, there's a little bit of an aside here. So C, D, E, just an aside. So when blocks oscillate on a spring, just so you know, the position function is going to be a sine function. And so there's going to be what I'll call an x max, or an amplitude, times the cosine of some omega times t. Now, we're going to review this a little bit later when we cover LC circuits, believe it or not, meaning inductive capacitive circuits. They also obey the same physics, believe it or not, that helps us study masses on springs. And I'm not going to prove this right now. We did it last year, but it turns out that omega is 2 times pi times the frequency. So there's a couple things here I want to point out. The velocity as a function of time is then going to be omega x max times the sine of omega t. I'll put a negative sign out in front. All I'm doing is taking the derivative here. And the acceleration as a function of time is going to be negative omega squared x max times the cosine of omega t. The thing that you've got to take as a given is that this is the equation for a mass on a spring, where omega is 2 pi f. So this is stuff that we've gone over, but it's been a little while, so it's okay if we're a bit rusty on this. This is exactly why we do problems like this, is to help us remember some of the mechanics that we went over and kind of forgot, since it's been a couple months. So with that in mind, notice a cosine is at its maximum value of, like, the biggest value cosine can have is 1. So what that means is the maximum acceleration we can have is omega squared times x max, because if you multiply that by 1, that's just the biggest value you can get, since cosine doesn't get bigger than 1. Okay, let's use this information in part C. So A maximum is going to be equal to omega squared times this x max. And I don't know if we even need to go this deep, but let's just draw a free body diagram. And we're going to basically say there's the upward force from the spring and the downward force in gravity. And we're going to lose contact when this net force is 0. So in other words, MA equals mg. So A equals G, it turns out, is just the answer we need. So luckily for us, so it turns out we absolutely need this result that we did here in order to do part D. So now what we can say is omega squared x max equals G. So that's 2 pi f quantity squared times x max equals G. And we have numbers. We know G is 10. We know G is 10. We know F is 0.0, let's go back. F is 1.8. So 1.8 hertz. And we know G is 10. So when we get X max, we will end up getting here 0.078 meters. Okay. Perfect. So, with that in mind, we can now move on to part E. E says determine the maximum speed of the blocks if the spring is compressed the distance found in part A. So what we can say is now V max is omega times x max, which is going to be 2 times pi times 1.8 times 0.078. And that's going to give us 0.87 meters per second. All right. So that is our answer to this harmonic oscillator problem. I hope that we can at least get A and B. C, D, and E are going to require a little bit of review. So one thing I want to say is the preview for when we come back from break is we're going to be looking at the physics of LC circuits, and we'll be reviewing simple harmonic oscillators as a result. So for those of you that are interested in systems involving springs, friction, shock absorbers, nobody in particular in the class, but it turns out a lot of times when we want to model systems that involve springs and friction and other things, what we'll do is instead of building a mass on a spring, we'll actually create them using combinations of resistors, inductors, and capacitors. But in the meantime, this is parts A, B, C, D, and E of the third question.